It's wonderful to be back in front of this group. I've presented for you all a few times over the years that we've been convening here in January. It's it's great fun. So today I'm very happy to present to you some of the work that we're doing in machine learning, specifically to improve our efficiency analyses and our ability to obtain asset information from our buildings. Have we got a clicker? Ooh, I'm in action now. All right. I want to acknowledge my team members in this work. Samir Tuzani and Reshma Singh are partners. External partners, we work on this effort with TRC. They are a utility program implementation company. With Signatron, they develop a lot of machine learning-based and data acquisition methods. NYSERDA, of course, a huge program implementer out of New York. And First Fuel is a building analytics company. So there are strong ties here to the actual deployment and installation of efficiency measures in the field. And I want you to hold on to this notion as I go through some of what we're doing in this effort. The very first thing I want to start with is recognition that we have today, and I've presented on this in the past, very powerful existing technologies available to building owners and operators to identify and analyze data on how can you improve the performance of your buildings. We can look at smart meter data automatically. We can pull data off of our HVAC systems and do continuous fault diagnostics. And the fact is that owners are using these technologies to great benefit today without machine learning, okay? Savings on the order of 8% whole building level with paybacks of 2 years just from analyzing data that's already available. So that's one world of reality. Now, on the other side, we're living in this world of data and information. And, you know, I'm sure like 9 out of 10 students you talk to, what do they want? They want data. What do they want to be? Data scientists. What are they very interested in? Machine learning, artificial intelligence. And the promise of what these new methods can bring is often talked about. In this particular 3-year effort, what we really wanted to do was bring that promise into a more concrete understanding. We talk all the time about new data, unstructured data, images, data we can get from our phones, text data. It's all over the place, right? And all the things we can learn. And so I'm kind of asking myself at the start of this project, yeah, but how is that going to make our buildings more efficient? What can we really do here? So that's some of the motivation. This is all the words on the page to describe that motivation. When we're talking about these new types of data that we want to fuse and apply learning techniques to, you know, traditional data for building analytics might be meters, weather. Now we're thinking about how can we take advantage of aerial and satellite images? What about LiDAR scans? What about thermal images? What about public data sets that are being disclosed more and more frequently, permit records, things like that? So the idea that I'll return to repeatedly throughout the talk is that of taking new data sources, combining them with machine learning analysis strategies, and using those to determine, can we enhance the tools that we already have available today? Is this going to take us a step further in the identification of building efficiency measures? And critically, can we do that in a manner that is cost competitive and practically viable with the techniques that we already use today? This is a 3-year effort. We're 1 year and 1 quarter in. So I'm going to talk some about an opportunity analysis that we did to really ground ourselves in what data is available and how can we use it. I'm going to talk a lot about developing new methods, and we're about halfway through that process. We're, of course, going to put these new methods into the field and see, are we actually able to materially improve over the technology that we have available off the shelf today? So I'm going to frame this in terms of what have we been able to accomplish in the first year of work. And let's talk about these three areas: the opportunity analysis that connects the dots between how we're actually going to use these new fancy sources of data, the development of basically toolkits that are replicable and open source workflows to leverage these new learning techniques and data that we can actually get our hands on. Not everybody is Google and Facebook that has the luxury of having access to these enormous volumes of data, nor cellular carriers and the like. I'll also talk about building a technical foundation for how we can deploy drone-based data acquisition and capture systems and use that to create very quickly and automatically 3D geometries of our building infrastructure. So opportunity analysis, the first place to start in this work was to very explicitly and methodically connect the dots between what data sources are actually available to us, what features can we extract from those data sources, how are those features going to actually be used in existing tools to improve our ability to identify efficiency improvements. And one needs to go through that exercise to understand where do you even start and cut through some of the hype. What is the actual opportunity here? So I'll give you some idea of the scope. We looked at 27 data sources out there. This could be public data or proprietary data or data sets that researchers are creating. We could look at all kinds of different features that you could extract from that data. Things like what equipment is on the roof. Things like what is the interior geometry of a building? What are the surroundings of a facility? And so on. All features that one could conceivably take machine learning or artificial techniques and apply at scale to extract. And then we map that into thinking about many dozen, about 70 types of efficiency measures that we know are commonly deployed in our buildings. Measures that relate to capital investment, to controls improvements, to maintenance, and so on. So this, the first thing we did, I'm going to start with mapping the measures to the data sources that are relevant to them, that kind of cycle of what we can actually do with things. So here's an example of just, being very methodical about laying out all the measures that we know are available to buildings, and then talking about what's the associated data source that we're actually going to use to automatically identify this measure. So just as an example, and this, in reality, the spreadsheet goes all the way down the page and across the floor because we looked at a lot of things. It's like, what if we wanted to think about, let's just take one, reducing envelope leakage. That's a big one. We could talk about things like outdoor thermal images or combining that with weather data from online stations, WeatherBug, and things of that nature. If we wanted to look at things related to lighting, same thing. We could start looking at, Wi-Fi data to understand occupancy. We could look at some of the data from the systems available in the building already. So we also went through notes on just what do we need to know to actually put this data to use. Once we had those data sources, we want to understand, okay, what's those features that we can really extract from them? And so this was also a process. And not only, data sources to features like a data source might be, what can you get from a publicly available assessor data? Okay, you could get building floor area, vintage, something about its geometry and its usage, right? But then we backtrack and say, all right, does this even exist really, or is it just research grade? Who owns it? Is it public, proprietary? What building types, residential or commercial, is it applicable to? Who might provide it? How do you get it? In this case, scrape from the web or connect to an API. These are all things that you have to go through to understand the practicalities. How am I actually going to use this stuff? We haven't even talked about our algorithms yet, right? We're just getting a handle on what is the opportunity. We could then take these features and map them into the types of existing technologies that we think they could be used to augment. And that is the kind of scope of opportunity analysis that we conducted. It took us about 3 months to get through this process. But from there, we could extract and really settle in on, out of all these data sources considered, which are really most promising for us to spend our time and effort in further developing. So satellite and aerial image data. Highly available, high potential to scale, and several sources from which we can actually obtain this data. Me and you, as just wanting to use data. Building footprint GIS data, that's out there. It's openly available for many US cities, not all of them. Relatively easy to extract and process. And when you combine it with these satellite and aerial images, which I'm going to show you, you can really build pretty accurate models using these machine learning techniques to extract, say, building footprint characteristics. That's really going to help us in our analytics. Third was drone-based, both visible and thermal images. The thermal side of our building operations and characteristics is really quite untouched in today's technologies. We tend to have data available from meters, from weather data, from systems that are operating in our building, our lighting controls and our HVAC. We don't really have at large a handle on the thermal side. So there's huge opportunity there to augment existing state-of-the-art. So the first thing we set about was developing these replicable and open solutions that we could use to extract features from satellite and aerial imagery. There is prior research in this area. The fact of the matter is that it's hard for you or I or my team or your students to take what's out there and run with it. To really understand what's the form and content of the algorithm, how is it trained, how is it tuned, and so on. Machine learning, some of these, say deep learning approaches is not like the typical kinds of traditional algorithms we're creating. You need significant infrastructure, you need large data sets to train against and validate against, and you need the time and know-how to tune the parameters in those models. They were put out there by computer scientists, not necessarily for the purpose of, pulling a footprint out of an aerial image for the ultimate purpose of building energy efficiency. So there's a lot of work to be done here. So I will step through the 3 things that we have put out so far that are going to be useful to us in developing and demonstrating these methods, but also to others in replicating and extending them. First is ways to develop training data with openly available data sources. Critical for testing an algorithm or developing one anew. A pipeline to test the deep learning algorithms themselves. There are many architectures to choose from. All throughout the literature. It's not, it's not like an ordinary least squares regression. It's a lot more complex than that. A third is the ability to post-process model results. We have to get these features into a form that they can actually be input into these measure identification tools. So let me step you guys through it. The first is automatic extractors of footprint data from GIS open data sources. And so we have tools that'll go out there and you can run the scripts. You can go to these existing sources, here, Analyze Boston, and through the code we've developed, quickly scrape that and pull it. Next is pairing that. So this is all about building a training data set, pairing that with a set of images. Who off of the top of their head today knows where to go quickly grab, 2.5 million aerial images that are matched with ground truth that you could train an algorithm against, or even use for your students in a course. So we've gone out and done that. There's a map box. We built an API. And we have paired then with the OpenGIS ground truth footprint data and those images for 14 cities and 6 counties, 2.5 million images. So here's the aerial image, here's the actual footprint. And what we do then is break that into a training data set for your machine learning algorithm to learn against, a validation set to check hyperparameters, and then a testing set to ultimately evaluate performance accuracy in working from an image where you don't know this and then creating this in an accurate manner. You guys with me so far? Great. So this is kind of a public service to provide that for folks. Next is the architecture of the reinforcement learning algorithm itself. So we've explored a couple that are out there in the literature that seem promising for this particular application. We've tested them against this data set. We've tuned the hyperparameters. And we're making this available open source. So you can go out there on Git. You can get it. You can further tune it if you want to. You can explore a different one using the training data set if you want to. And you can, in an open and objective way, compare performance. Third, this right here, this kind of thing, this footprint or mask or tile isn't really what goes into an analytics tool. My meter analytics tool doesn't really want this. My simulation tool that gives me efficiency measures doesn't use this. So we have then converted these outputs from the machine learning model into actual polygons with geographic coordinates, so like GeoJSON type formats that are then usable by existing off-the-shelf technologies and all the other tools that building energy folks like to create. Okay, so that's area one. The second, I want to talk about this foundation for drone-based generation of 3D geometry. This has been really fun. So current practice for getting 3D building geometry information, there's some data portals, there's some extraction using aerial imagery. When we move to thinking about drones, we can get much higher resolution. We can be a lot more accurate in the geometries that we are building up. And when we throw a thermal camera on those drones, we can get insights into the envelope that none of the other sources are really able to offer. Not to mention, it's very fun to fly drones and see how we can fit them out and augment them for research purposes. We had to design the drone system, define the data capture and acquisition methodology, and start, again, this workflow. How do you automatically extract the 3D? And so this is what it looks like. So here, hopefully folks in the back can see this. This is like a building with its footprint. You plan your flight. You program the drone software. Now, for our purpose, we want to fly these sort of overlapping circles. So the whole time we're just going snap, 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 snap. We're taking pictures and we're moving over that space in a known pattern. From there, we are then able to get this 2D imagery. So you have all these different sort of perspectives from your overlapping circle and flight of pictures that you've taken. From the 2D geometry then, we build what are called 3D point clouds. This is photogrammetry methods that allow us to get to the 3D representation. So here I want you to think about just a whole cluster of points. It's like, the 2D version is like you do like pointillism in art class in high school, but this is now the 3D version. So where you have very dense, like where you have dimensions or axes of high density, that's like going to be a wall. So this is all done now through some manipulation of basically software that's already out there. You have to get it in the right shape to do what you want. But this is some of what's available today that, say, wasn't available 10 years ago, and is very exciting on the sort of computer vision side of things. All right, now once we have these point clouds, we can move into extracting an estimate of this building footprint. So you see the black and the red, it looks a lot like this picture we started with. We can also estimate from those point clouds the building heights, and this is sort of a heat map that shows you that, and we put them together and have our 3D polygon representation of the model. Okay. Now I want to talk a little bit more about this middle piece and this point cloud and how we actually get there. So we first take our 3D, we slam it down into a 2D projection. That's the very first step that we take. And then we're going to do some mathematical transformations on that 2D projection, specifically a Huff transformation, to extract all the line segments that are probably walls. From there, we turn that into polygons. Okay, and so now you can see we've kind of gone, it's almost like we took a little bit of a step backwards, but not really. The resulting polygons then, after we merge across all the data we have, is then getting us back to really the polygonized representation of this initial just kind of projection where we weren't quite there yet. And then we take from the point clouds the height of all of those lines, and we can get the heights of each of these merged polygons. And that's really where we need to be to feed in the information, again, to these existing analytics tools. That's what they want. They don't want this, they can't do anything with this point cloud, even though it's really cool. So that's been our kind of the path that we've traversed over the first year and some of work. Is we got grounded in really cutting through a lot of the hype, and specifically for a very grounded application, what data sources that are new and cool are actually going to do me any good for identifying efficiency measures? What kind of machine learning algorithms can I actually use to extract those features that I want? And how can I represent those features or transform them into a format that can actually be used as an input to an existing analytics tool? The other dimension of that is, how do we move beyond the things that, say, Microsoft has done? People may have heard that, oh, they put out footprint data for every building in the United States. Well, how can we introduce a degree of openness and transparency that will allow others to replicate these methods? So going forward, there's still 2 years of work to do, but we have an exciting start, certainly. There's some work to do here that's just underway now to actually, get the URL on Git where you can go and access some of these training data sets and tuned models. On the drone side, we'll do things like extract more features, window to wall ratio, the thermal imagery and thermal heat maps with the thermal cameras that we'll be adding. Again, published the intent to make this all open source. And we'll also look at new data sets. So far, satellite and aerial images, drone RGB images, drone thermal images. We can look at oblique image data sets. We can look at LiDAR, and we can look at other information out there. Our colleagues are looking at, say, building permit information and that nature that requires data and text mining kind of data as a complement. At the end of the day, we always have to come back to reality. Like I said at the start, is this practically viable? Not just like, can we do it? Can we make it work? But does it materially advance the capabilities of today's technology? does it do so in a cost-effective manner? That's going to be a lot of the testing that we do in real buildings in out years of the project. So we'll want to take, to be very clear, an existing off-the-shelf tool. We'll want to run it on some buildings, understand what efficiency measures we get. We will then augment it with these new data sources and machine learning feature extraction approaches, and then see what kind of measures do we identify for those very same buildings. We'll see how much human labor time did it take, what was the cost of that acquisition, and so is there a strong technology delivery value proposition going forward. This is my prepared remarks. I would thank you for your attention and open it up to any questions that you might have. Yes?
I was wondering, I'm not familiar.
Oh, you have a mic. You have a mic to capture questions.
I'm not familiar with LiDAR equipment, but is it possible to do that with the drones and avoid a lot of the kind of reestablishment of boundaries from all the from the optical images?
We haven't yet started that. The work that our partners and others have done has been very ground-based, either on vehicles or just our partner at Signatron, a company here is UC Berkeley professor company, where they've used, in collaboration with researchers here, actual mounting on people and walking through a building, say to get internal geometries and things like that. So I don't really know. We will.
Just thinking of another cool thing to mount on a drone.
Yeah, yeah.
Hi, Jessica. I really enjoyed your presentation. I was wondering, as you're developing out your programs, as you're developing these tools, what has been the discussion among your team and your partners in terms of whether or not this will ultimately be open source or whether or not this is going into a pay company? The only reason I ask is I've tried to use similar types of services before, and when they're in beta, it's great and it's a wonderful education tool. But eventually that goes away, and now there's no licensing for education. It's all the pay customers. So just plug if this could be available to educators as you develop it, or the tool sources or the data sets. I think a lot of us in this room would probably use this type of information in our teaching.
Great. You ask a very timely question. A lot of what we do is open source. A lot of that is driven by what's really going to fuel the highest degree of uptake. That's usually the starting question, is what's the model that's going to get this into use? So we don't often actually start with open just for the sake of open, even though that would be, it's about impact. So how are we going to get these methods into use? And will that be through making it open or through other mechanisms, right? So a lot of the times it ends up being open because that's just how it pans out. Here our intent is open. I submitted an open source license request to our IPO office here. That's funny. It's like you work here or something. But actually, so I'll get to the punchline. Actually, what they told me was, hey, there might be some kind of commercial element here. Let's actually talk about this more. However, let's keep the door open to having, free research availability. And so, then you get into the myriad options of how you make something available, to whom you are making it available, and under what conditions. So I still think we have a research and academic path here for some of this stuff, and we will see. Those conversations are forthcoming. Thank you for the question. Both of you, it's like you know me. Yes?
Oh, it seems to me like we're at a point where all this data, very specific and complex data, is about ready to explode. I remember like when I was at a TED conference and Sergey Brin was talking to this guy who I know about Google Earth, and the guy said to Sergey Brin, it would be wonderful if I could draw on top of Google Earth with SketchUp. And within a month, I heard they bought that program because they knew the importance of having those 3D models in the citywide. So I look at a city like New York City, and all those, like most of the cities model the footprints 3D, and I see people using that for apps and programs for developers where they can mine and see where the capacity for further development is, as well as the kind of air rights and stuff like that. So this is on a very high level. But on top of all that stuff, all new buildings are pretty much done in BIM and Revit, so they're very complex models already there. So with all this happening on the underside, I mean, are you leveraging this sort of thing, or it's not out there to the point where you can use it?
I kind of get where you're going.
Yeah.
So a lot of the devil is always in the details of what was the original intent of that particular model or representation, and who can use it for what purposes. So say the existing 3D models for New York City might be great for New York City for developers, but they are not easily input and available at the resolution that I need to figure out for one particular existing building, can I automatically now generate the most relevant energy efficiency measures for that particular building. So then we look to other ways that we can augment that. Next, maybe, and they're not always, there's interesting things about New York City. They're always not so precise. And so the things you get, for example, in the Microsoft data set that we know is like you get whole areas where you just get a big lump because everything's so close together. They can't get the edges between them. So there are places where you can use things for one purpose but not another. As far as BIM models, there's a real issue there with chain of custody and who gets that, and is it maintained, and is it available to whom, and
Who
so
owns
on.
it, yeah.
Yeah. So,
But they,
Came out in the building, or was it just what the architects?
well, yeah, it's a whole other can of worms. Does it reflect what is actually there? Yeah. So I think though the at the kernel of your question is something around, you know, through all of this development, are we appropriately leveraging where we can? And are we filling gaps in a way that are expanding people's ability to make use of this information for new and different applications?
yeah, all those BIM models are embedded with energy efficiency models to begin with, right? So it seems to me like if you had a real small city, 5 buildings, and you had 5 buildings all, and you had all that data, that would be perfect, and it was all standardized. But I'm wondering if there's an overall view of like that sort of level of standardization to make the data more consistent and accessible. I mean, this would be a wonderful thing, right? Because this would enable
would be a
cities to
wonderful
achieve
thing.
their 2050 plans and stuff like that. But and that's part of the problem, I guess. We're spending so much time getting data, right? That may not be, I don't know.
I'll take one last question. I think my time's up. Yes.
For the infrared. What? Okay. For the infrared, are you using a DJI FLIR? What were you using to do that?
We have not yet overlaid the thermal camera into the drone acquisition system. And I don't know which specific camera we have spec'd for that.
Okay.
You can send me a note. I can get back to you though.
Okay.
This guy Samir is the one who will know that in his sleep as he's looked at all of them and spec'd them out.
Okay. Thank you.
Okay.
One last question, Jessica.
Yes.
Could you comment just on the future of AI, and is it, cut through all the hype, and how practicable is it to integrate these data sets, and will it really give us advanced information?
This is one of the big questions of the day for us in our field, which is in what ways will the promise of AI manifest? And I will often, so many of us, like, Marianne's written a 6-page paper about this recently. We're all kind of pushing from different angles to understand what is that opportunity. I I often think in terms of like analysis, control, and prediction. We can think also along the dimensions of where I mean, this is for me personally. Other people will have different kind of mental models and takes on it, but I think often about the ability to improve performance of a specific facility over today's state of the art, right? And how far will AI take us there? And there's a different consideration, which is we know that in our industry we have a huge problem of scale, that there's wonderful things that we can do for a building that we have yet to be able to scale across all buildings in the way that we would like. And so for me personally, I'm most intrigued by the promise of AI to scale existing best practice in a way that is not possible today. And that's in contrast to improving best practice from, a 95% to a 100%. And there's certainly, a lot of active interest in all of those areas. I think that there's obviously a huge agenda for predictive and policy or goal-driven control. And so I'll stop there, but I think there's huge promise in scaling. Optimizing our optimizers through the use of AI is of less interest to me as a researcher, but there are also folks who are looking to see how far we can go there as well. Time is also an important dimension. So what is AI going to do for us in 10 years versus 30 is totally different questions. And I don't feel well equipped to think a lot about AI 30 years from now. Think about where we were 30 years ago. Anyway, there's some initial thoughts. We talk more at lunch. Thank you.
Thank you, Jessica.